Today, I will show how we can use a big data machine learning approach to study the model parameters of ruthenium chloride in using thermodynamic high magnetic field data. This work is in collaboration with Kimberly Modick and Brad Ramshaw and was supported by the NSF. Ruthenium chloride is a candidate quantum spin liquid material which has all the properties of a classic frustrated magnet with a paramagnetic phase at high temperatures, an intermediate phase that is correlated in some way, and a low magnetic ordering that sets in. But it is particularly exciting because in neutron scattering, spin-on continuum, diffuse scattering, whatever you want to call it, was observed and suggesting that it really is close to a quantum spin liquid phase. There have been many studies now on the parameters of the spin model, and the dominant parameters that we've been focusing on are the Kitaev coupling constant K and the gamma constant. But there's several other ones. There's that are subdominant, the J and the gamma prime, and J3, the third neighbor interaction. And one example of such a study is a recent neutron scattering, which really focused on the K and the gamma, a collaboration over time, you might say, between a numeric theory group and a neutron scattering group. And the neutron scatterers were able to definitively show that we must have that the Kitaev coupling is negative, and in addition, that the gamma coupling has got to be way out here, almost of the same order as the Kitaev coupling. Here's some other, this is a theory example where they looked at the magnetic phase of the, that is predicted in a tensor network approach. And so you could try to map the phase diagram and use that phase diagram to sort of infer the parameters. And it turns out to be actually an incredibly sensitive test because here these authors needed to put gamma prime equal to 0.03 in addition to K and gamma in order to get this phase diagram. If they remove this gamma prime equals 0.3, then the zigzag phase, the important zigzag phase, disappears completely, and it's dominating the phase diagram now at gamma prime equals 0.03, but then it disappears. And here's another recent study with high magnetic field, and they used a DMRG to compare with the high magnetic field data that they took, and they were able to infer a phase diagram as well. And they also needed some dominant couplings. So maybe we need a new direction to try to solve this problem. And today I'm going to talk about high magnetic field data. And high magnetic field is known from other studies. Here's a study of ytterbium titanate, which has a diffuse scattering at zero magnetic field. But as you crank up the field, you get spin waves. And the authors were able to pull out the parameters of a Hamiltonian from the spin wave data. So high magnetic field really helped solve the problem in this case. So we would like to do the same for ruthenium chloride. And so I was able to collect a database of 3 different kinds of high magnetic field data. So here is magnetization data. Here is torque data, which is magnetization cross H, and it was one component of that vector. And here's the derivative of that torque with respect to the field angle. That's called torsion. And these data were taken by Brad Ramshaw and Kimberly Modick, who are my collaborators. And this data was taken from this paper. And this has been all previously published data. And together, putting this all together, I was able to get 213,000 data points that are 4-dimensional. And now we need to apply a big data approach to get to infer these parameters. And here's what I did. I developed a neural network, which is time reversals covariant, so that if I change the size of the field, it gives the same prediction in the output. And this network maps the thermodynamic state and a thermodynamic state to a set of coupling constants of a model. And so here, these are the G factors, and these are 2 coupling constants of the mean field theory, which are related to K and gamma. And the one additional input is the category of the data that I would like to study, that I would be studying. And the categories you say might be magnetization, torque, or torsion. And then we feed the output of all this information here into the mean field theory, and it makes a prediction for that category. And then you can compare that category to the actual data and use define a mean squared error loss, and then backpropagate through mean field theory and learn the parameters of the model. And I was able to backpropagate through mean field theory by solving the mean field theory using PyTorch. And I found this nice method on Stack Overflow, this nice code for using Newton's method that I could use to solve mean field theory. And then I have a working machine. And so here are the results, the magnetization. You can see the way that this machine works is it can almost perfectly fit the data, but it does so by continuously varying the coupling constants as a function of the thermodynamic state in order to get that good fit. So here, if I freeze the value at the end here, and I just fix the value that way, then I would get this green curve, which I'm calling the mean field theory model alone. So you just fix those parameters, you get the green curve. So it has to bend the green curve into this orange and blue curve here. And here's the bending in the parameters, and you can see we get positive gamma here and a negative Kitaev coupling, and we get a G factor of around 2. These are relatively consistent with what we with the neutron scattering data that I showed you earlier. The torque data is a little more confusing. At 1.3 Kelvin, it's really low in temperature. Maybe it's much more quantum, and maybe the mean field theory is much less valid in this regime. And the end result is we have kind of strange small values of the coupling constants in this region, and unexpected values of the G factors. So we can think of this as the theory is we're normalizing the coupling constants in order to match data that's maybe far away from the high field, very high field limit where the mean field theory might be more valid. The torsion data back at 20 Kelvin, we can do a sweep and we can get, again, relatively nice parameters here. The gamma now here is negative on average, but you can see that it's very close to 0. And so, maybe, yeah, it's not giving a gamma here that's of the same order of K, like the neutron scattering. And also the sign wasn't positive while this was negative. But nevertheless, maybe this is also still in that effective parameter regime, because here the field is not that high. It's 35 Tesla. But so then let's look at data that goes out to 60 Kelvin. And here, way out at 60 Kelvin, we can see that the parameters sort of flatten out. And then when the parameters flatten out as a function of field, you can really start to feel like you trust the results. And it finds that the G factor is, it's around 1.2 here. Maybe that's not so unexpected. And the difference between the Kitaev and the gamma constant is about minus 45. But now if we go to higher temperatures, 40 Kelvin, we see that actually the G factor stayed the same, but the difference between the coupling constants doubled. And we go even higher. Now we're getting close to maybe too high, but the coupling constants again increased. And so actually we can, it seems what's happening here is the coupling constants are scaling with temperature, and this together is producing a scale invariant prediction for the data. Now, why would I believe it? You have to read this paper on. It's already known actually that the torsion data which we're studying here in this intermediate temperature range between 20 and 80 Kelvin collapses on itself, and it's just a function of h over t. And as a result of that scale invariance, this model is learning. It is scaling the coupling in order to keep its predictions scale invariant. And notice that it prefers to have the coupling to be some large finite value. You have to divide. If you divide this by temperature, you can see that it's roughly K minus gamma divided by temperature is roughly the same for all three of these plots. And so it's holding K gamma over T fixed, and that's what's giving it a function of H over T. Its prediction is a function of H over T. And so we infer from this that it needs to have a finite coupling in order to match the data. So it's a data scale invariant, not from some fluke that these K minus gamma might have canceled out and we end up with essentially a non-interacting scale invariant theory. That's not what's going on. We're showing here that actually there's an emergent scale invariance in this system that is this interacting, and the interactions are playing a strong role in that in this intermediate temperature region. So in conclusion, we've studied high magnetic field data to solve the parameter inference problem of alpha ruthenium chloride. We've been able to merge mean field theory and neural networks and infer a mapping between thermodynamic state and the coupling constants of the problem. And we obtained data with results which are not too different from previous results, but with the surprising observation that the intermediate temperature regime, this Kitaev paramagnet, which is not a conventional paramagnet, is scale invariant in a way in which interactions are playing a strong role here, and it's not some effectively non-interacting kind of thing for the torsion data. With that, I thank you for your attention. Please don't hesitate to ask any comments or questions in the chat if there is a chat, or otherwise maybe you can send me an email.